Good afternoon, everyone. Welcome. It's another in a series of talks that I'm going to give. Actually, I think it's the third out of what's going to end up being somewhere in the neighborhood of 14 that I'll be giving over the course of the cruise. And I'm Don Campbell. And anytime you see us, anytime around the ship, Susie and I love to talk to people, so please feel free to come up and talk or chat or throw fresh fruit or whatever. We really enjoy that. Not so much the fresh fruit, but anyway, we're always available. Now today we're going to talk a little bit different. This is actually a destination enrichment talk, only if you're an alien coming from Mars or Alpha Centauri. But basically we're going to talk about our geologic world, and we're going to talk about the evidence of continental formation and drift and all that stuff that'll be abundantly obvious as we continue on through our journey. And Africa, right now, as we speak, is forming another continent. And when you think about it, when I show these things as we go along, you'll see that basically all the continents that exist today came from Africa. Anyway, more on that new continent in a few minutes. But just as kind of a precursor, don't go out and run out and make a lot of real estate investment in that particular area yet, because that incident may be a million years or so away. Now this photograph, it's a beautiful photograph, and it was taken from space, and that's what we call home. It was taken 40 years ago by the Apollo astronauts. Can you believe that? Just think, they were in a soundstage in Hawaii when they took that picture. Now, they might have even been in Hollywood, I don't know. Anyway, the oceans and continents are driven largely by forces that are pulling and pushing the earth and the land every day. It's a constant ongoing thing. And as the continents spread apart, the seas widened and deepened. Now we're going to talk a little bit about how that happened. And I'm going to cover about 4.5 billion years in the next 40 minutes or so. So it's going to be kind of a little flash. The breakup and formation of large bodies of land appears to have been pretty cyclical throughout Earth's history. Pangaea was not the first supercontinent to form on Earth. Geologists today believe that there may have been 2 or 3 even before that. But it is the one that geologists usually identify as the starting point to the breakup into the smaller continents that we know today. Now, Pangaea existed during the Paleozoic and Mesozoic eras that began 250 million years ago. So we're talking that we've already leaped forward from 4.5 billion to 250 million years. Anyway, the continents as we know them began to form when Pangaea broke into 2 big supercontinents called Gondwanaland and Laurasia. Africa, South America, and Australia became Gondwana, while Europe and North America became Laurasia. Actually, I should say were Laurasia before they became what they are now. And we're going to see how this was kind of determined by people in time. In order to really understand it, we need to go back to some very early ideas about the Earth's formation. Back in 1596, a Dutch map maker named Abraham Ortelius thought that the Americas were torn away from Europe and Africa by things like earthquakes and floods. In his map that's shown here, you can see that the east coast of South America is a near match for the west coast of Africa. Although more fragmented, if you kind of push North America and Europe together, you can also see a fit up there, although you kind of have to twist them a little bit. Now, Ortelius speculated that the coastlines of the continents fit as if they were pieces of a jigsaw puzzle. Then in 1858, the Italian geographer Antonio Snider Pellegrini drew this map. He was influenced by Ortelius's earlier work. Why it took so many years before somebody else came up with it, I don't know. He furthered the concept of how South America and the African continents once fit together. An Australian geologist named Edward Seuss, no, not the guy that did the Cat in the Hat. This guy was a geologist. His name was Edward Seuss, and he called the landmass that was made up of South America, Africa, India, and Australia Gondwana, and that was back in 1895. Now, he named it that way because of some of the earliest rock formations that were first investigated in part of the Indian region had the same name. Seuss based his deductions on extinct fern fossils that were found throughout all of the continents. There are even remnants of that particular fossil in Antarctica. Amazing. A fern that once lived in Antarctica was also in India? Wow. Ironically, it wasn't until about 50 years later that a German meteorologist, you know, kind of the guy in the evening news that comes up and points at the map and tells you where all the storms are, his name was Alfred Wegener, and he theorized that there was a large landmass that Gondwana came from. He referred to the writings of people like Ortelius and Snyder Pellegrini, Seuss, and others, as well as some of his own studies. Wegener named this Pangaea, coming from the Greek term for earth or entire earth. Wegener believed that Pangaea once covered the area from the South Pole to basically near the Arctic Circle or even up as far as the North Pole. He theorized that it subsequently rifted or broke apart. Now remember, he was a meteorologist, so he was attacked from the very beginning. Geologists at the time believed that Earth's crust was a very hard, rigid, rocky plate, and they thought that the land was changed only by weather, erosion, earthquakes, and volcanoes. They just couldn't accept that the crust was made up of moving plates. And after all, Wegener was just a weatherman. Alfred Wegener did raise many questions, and among them were, why are coal deposits in Antarctica when they were created from plant debris in tropical jungles? Or how did similar plant and reptile species show up on both sides of an ocean? Now, Wegener saw similarities in rock structures and fossils found on the coastlines in South America and Africa. Other parts of the world that were widely separated featured similar findings. He theorized that it was not possible for those animals, plants, and rocks to have moved across such vast bodies of water. I had to kind of agree with him because I haven't seen very many swimming rocks. Now, I know there is rock that floats, but usually it's just small things that come off of a volcano, but they really don't have much of a freestyle to them for getting across the ocean. Basically, what he said is all of that evidence said that the land had moved. The movement of the land masses was caused by what Wegener termed as continental drift. Now, this animation shows his concept of that drift. Crustal plates formed hundreds of millions of years ago have been slowly drifting about the Earth ever since. And I can guarantee you, folks, it's not that fast. It's a lot slower than that, because if it was that fast, we'd have a hard time just standing up. In 1930, Alfred Wegener was lost up in Greenland and most likely froze to death during a meteorologic expedition. But soon after his death, his theories were all verified. Wegener's idea was a major breakthrough in our understanding of the Earth. He believed that the study of how the Earth was formed and how it changed over time required all of the sciences, not just geology. Wegener turned to disciplines from anthropology to seismology and even zoology to verify his theory. Continental drift can best be explained by understanding the Earth's composition. Scientists describe it as having a crust, a mantle, and a core. The crust is the outermost layer, and it's rigid and very thin. It is brittle and it can rupture. Actually, it has ruptured many times over history. The crust under the oceans is about, maybe 3 miles thick, and under the continents it averages about 7 times that, some 21 miles. Under some of the mountain ranges on Earth, the crust could be as much as 60 miles thick. Now, beneath the crust is the mantle, and that's a dense, hot layer of semi-solid rock that's about 1,800 miles thick. In that layer, both temperature and pressure increase with depth. The upper layer of the mantle is cooler and more rigid than the deeper layers, but it's that convection of temperature and rock inside of that layer that creates an awful lot of the dynamics of the Earth that we know. Way down in the center of the Earth is the core, and it's about twice as dense as the mantle. Again, it's made up of 2 parts. The outer part is liquid, and it's very hot. And the inner part is solid, and it consists mostly of iron. And it is that solid iron core that gives us our magnetic field. It's like a big Boy Scout magnet hidden real deep in the Earth. In 1927, Alexander Dutoit proposed that Pangaea broke into Laurasia in the northern hemisphere and Gondwanaland in the southern hemisphere. In it, he strongly supported Wegener's theories that the plates had drifted apart. He believed it began about 225 million years ago and that it took, just a brief 100 million years to complete. The splitting of Gondwana and Laurasia from Pangaea caused a shield volcano at what we know of today as the Reunion Island in the Indian Ocean. It's one of the most active volcanic sites in the world. Eruptions there have lasted for over 30,000 years. It last erupted, by the way, in 2010. And we'll be talking a little more about hot spots in a few minutes. And also, when we went to, here in Sao Tome and Principe, you were actually at a volcanic island that was based on a hot spot. When Gondwana broke apart, South America, Australia, Antarctica, India, and Africa started to form and drift apart. Actually, Africa never went anywhere. It just kind of sat there while everybody else moved away. The Seychelles and Madagascar were still attached to one another. A huge eruption about 65 million years ago occurred as India passed over the Reunion hotspot. Scientists believe that's when Madagascar and the Seychelles were separated from the Indian subcontinent. The Indian plate charged northward toward the Asian plate, and it could move faster now because it got rid of all that dead weight called Madagascar and the Seychelles. It was now going at a rate that was the fastest movement of any known landmass. The Indian plate moved northward at about 7 inches a year. Now, in geologic terms, that's light speed. That is really fast. The Asian and Indian plates ultimately collided. The Himalayan mountains are a product of that fender bender. Now, when plates meet, there's a whole bunch of different things that can happen. One can slide alongside the other, one can be pushed down under another, or they can just collide together. Now, basically what happened with the Indian plate moving north is similar to what happened to create the Andes and the Alps. It's where two plates have come together and they push against each other and one doesn't get subducted. That causes this thing to drift, to push up. The collision actually slowed the Indian plate down quite a bit. Today it moves at just a creep only about 2 inches a year. So you can see there's a huge difference. Now when you're talking a landmass the size of India, it's a little bigger than the lot that my house sits on. Actually, it's a lot bigger, and it has billions of tons of earth that's moving. Now, each of the future continents that broke away in that particular time carried with them several species of flora and fauna. And one example is the flying fox that pretty much remains common to all the continents and land masses that were once connected. Several of our ports of call are in the Gulf of Guinea. That's circled here in red. The Gulf coastline forms part of the African tectonic plate, and that corresponds to the continental east coast of South America. The coincidence between the geology of South America and Africa is one of the clearest confirmations of the continental drift theory and the existence of tectonic plates. Dutoit wrote, quote, "A geological comparison of South America with South Africa" in 1927. In 1949, the year after his death, the Geological Society of South Africa inaugurated a lecture series in his honor that they still do today. So what's all this talk about plates? Well, plates are really large chunks of crust that make up the Earth's surface. Today, there are 12 very large and many very small Earth plates. They developed very early on in that 4.6 billion year history of Earth that I talked about a while ago. Now, as I said, they can collide, they can pull apart, they can slide alongside each other, and the drifting of the plates is called plate tectonics, which comes from the Greek root word to build. Now, it's that plate movement that causes such wonderful things as earthquakes or volcanoes. Without the plate movement, we would just be sitting on a very stable, not very dynamic Earth. This is a graphic of where an oceanic plate is being pushed down beneath a continental or a dry land plate. Sometimes when the two plates meet, they don't crash into each other, and one of them may be pushed down under the other in a process that's called subduction. Now the plate material that's being pushed down gets pushed back into the mantle, which is just under the Earth's crust, and when it gets down in there, it melts and causes all kinds of things to happen, including, among other things, from volcanoes on the upper crust that's being subducted under, as well as causing that shrinkage of the plate itself. Most volcanic islands around the world are found at the boundaries of plate tectonics. That includes the Azores, and they were created when the European and the North American crustal plates started to pull apart. Now, as the plates pull apart, molten rock broke through the seafloor and built an undersea ridge, and the lava built up and created the islands. Now, if you want to see a really clear example of this, just go to Iceland on your next cruise. And in Iceland, you can actually put 1 foot in the American plate and 1 foot in the European plate. And if you stand there for, 10 or 20,000 years, your feet will actually start to get pretty far apart. And you can't really feel it, but it's really evident when you go there because you can see this very distinct crack that goes all the way across Iceland. Now, the Madeira Islands, the Canary Islands, Cape Verde, and the Azores are part of what was called the Micronesian archipelago. They have peaks that are about 1,860 meters, somewhere around 6,100 feet for those of us that have a metric challenge, and they are all of volcanic origin. The Micronesian archipelago is about 1,700 kilometers or a 1,000-mile long line of volcanoes. And basically, you could follow those volcanoes up, looking at the age and the height of the volcanoes and so on as you go along. Now, it was not formed at the boundary of a plate, similar to the way Iceland and the Azores were formed. It was formed in kind of mid-plate, and it's a thing called a hotspot. This volcanic archipelago was formed as the African plate moved over that hotspot. All right, what's all the fuss about hotspots? Well, I'm going to kind of tell you. Anyway, to understand it better, it's easier to understand Hawaii. The whole Hawaiian chain that goes all the way from pretty close to the Aleutians down to the southeast till it gets to the main islands of Hawaii that we know today, actually came out of one place in the Earth's mantle where the Pacific plate was moving across that mantle. And that's an excellent example of how all this stuff works. Now, the hotspot, as I said, is located in Earth's mantle. It's generally found somewhere around the middle of a plate. And molten magma from the center of the Earth is pushed up against the bottom of the plate. And the plate moves, but the hotspot, for some reason that the geologists don't really understand yet, the hotspot itself doesn't move. In the case of Micronesia, the hotspot's been active for maybe 70 million years. Now, when a weak spot in that crust starts to occur, come over that hot spot, all of a sudden magma will come up through the crust itself. It'll break itself through, and then very hot, very liquid lava comes up. And then as the plate moves off, we'll move it off that way, basically the hot spot cools and the volcanic activity ceases, and then it moves over till another weak spot happens in the crust, another volcano occurs. Now, this whole thing happens where things are moving at about 2 to 3 inches a year. So when that comes and goes, it spaces those islands out. And if you look at Hawaii, that whole chain of islands that goes all the way out past the Marshall Islands, you'll realize that that has taken place over millions and millions of years. And again, like I said, when another weak spot in the crust passes over the hot spot, activity starts up again, and you got little Lohi that's sitting out off the coast of Hawaii right now. It's just breaking the surface, and in a few years, it'll become a full-fledged island. And that you might be able to get some real estate deals on in the not too far distant future. In Cape Verde Archipelago, the islands were formed on those hot spots. They're younger at the western end because of the plate movement over those spots, and they have been dated to be about 180 million years old. Fogo is the youngest and most active volcanic island in the chain. The magma chamber there is maybe only about 5 miles below the surface. So when it wants to bubble up, it doesn't take long to come up and create a new pile of land. Mount Fogo itself is the highest point of land in the archipelago, and it reaches an elevation of about 3,000 meters or some 9,000 feet. The caldera for that volcano is 8 kilometers, or about 5 miles in diameter. This mountain, Mount Fogo, erupted in 1951, 1995, and last year in 2014. And the most recent of the eruptions of that volcano ended just in February of this year. Fogo consists of one single volcano, so the island is nearly round. When you look at a space picture of the island, it looks like a big disk in the middle of the ocean. That's only about 25 kilometers or 16 miles in diameter. There's a very large caldera that's located toward the northeast corner of the island. It's surrounded by very steep, near vertical walls on all sides, but the east, where the lava can flow, is kind of more gentle. There are fissures along the western flank that were created sometime before 1750. And the current shape and topography of Mount Fogo is from the sliding of the eastern flank toward the Atlantic Ocean. There is a little bit of a risk here, however, for those of you who live in Florida, South Carolina, North Carolina, Maryland, Washington, New York, all those coastal places on the East Coast. Because if the eastern flank of the Cape Verde Islands decides to drop into the Atlantic, it will create a tsunami. That's a big pile of water that will come across the Atlantic at somewhere between 500 and 700 miles an hour until it finally reaches the east coast with a wave height that will be, depending on which one of the geologists and the oceanographers that you want to believe, somewhere between 50 and 150 feet high. So those of you who live in Miami Beach with an average height of your basement 6 feet above sea level probably are going to get wet. Anyway, it's probably something that we don't have to worry too much about because it's predicted to happen sometime within the next maybe 300 or 400 years. So I don't think we have to worry too much yet. The Cameroon volcanic chain was also formed by a mid-plate volcano hotspot. And this one is geologically unusual because it extends through both oceanic and continental crust. So it both comes out into the water and goes all the way up into the Cameroons. Now, various hypotheses have been advanced to explain how that line occurred. And it may be really more caused by a more complex interaction between the hotspot and the African plate. So you've got this plate that's been moving around and a hotspot that sits out there. And so they're not really quite sure what it is, but they know that it's unique compared to all of the other hotspot activities in the world. Anyway, in this event, the chain covers a very long distance from deep into continental Africa through the bight on the coast that creates the Gulf of Guinea. Now, the bight is basically just that big bend or curve that sits there alongside the coast. The country of Sao Tome and Principe is part of that Cameroon mountain chain. Pico de Sao Tome is a shield volcano that's on this chain. And this type of volcano, if you think about the volcanoes in Hawaii, they're normally created by a very hot, very liquid, very runny lava. They don't generally do these big eruptions like you've seen at Mount St. Helens and Pinatubo and stuff like that. They just kind of bubble out of the ground. So they make this big, long, slow, sloping kind of a hill. And it usually looks like an old ancient warrior's shield laying on the ground. Well, in this particular case, the center column represents where the central vent for the volcano was. And originally, it was that big shield that went all the way from the top of that point out way to the edges of the volcano. But over centuries, over hundreds of thousands of years, erosion and weathering broke that volcano down and changed the shape so that now all that's left is that big spire. Basically, the lava flows here went out so far that the whole island system was created by one particular large, gigantic volcano. Most of the lava that erupted here over the last million years was basalt. And I talked about this a little bit when I talked about Sao Tome. Now, basalt is essentially a hard black volcanic rock because it has low silica content. It has a very low viscosity. And therefore, basaltic lava can flow quickly and move more than 20 kilometers from a vent. That's about 12 miles to me because I have to write that down because I can never remember it. Anyway, basalt is one of the most important rocks in the Earth's crust, and it shares many of the characteristics with granite. The best place to see it, for those of you that got a chance to go out there, was at the Boca do Inferno blowhole. That means mouth of hell. Basically, because of the shape of the island, there's a big underwater cave that goes all the way in underneath this thing from out in the ocean. And as swells and waves come into that cave, that basically has no place to go except at the far end of the cave where there's a hole in the surface and the water comes gushing back up. There's blowholes like that all over the world, by the way, so you don't have to go back to Sao Tome if you didn't see it during this cruise. Now, though Cape Verde Islands are almost all of volcanic origin, they vary widely in their terrain. As a great amount of erosion has taken place, and there's still some craters that remain there. The highest point is Mount Verde with an altitude of about 725 meters, or some 2,300 feet. Today, the mountain consists of a reddish-brown rock that's debris that's caused mostly because the iron content in the rock has rusted over time. It leaves it this red color, and it's basically going to stay like that forever now because of the dry environment. So what happens after volcanoes stop their activity? Well, erosion is one of the great shaping forces that our Earth experiences, caused by water, by ice and wind. It grinds away the rock and it breaks it down into soils and sand. Among the best examples that, in my mind, are the great canyons and fjords that are found all around the world. If you look at the walls of the Grand Canyon in Arizona, geologists are able to determine the history of the Earth. And you could see that by going down layer by layer by layer through all of those layers of rock over millions of years that have been exposed by the Colorado River. The most prominent place to see and photograph erosion during a cruise was at Angola's Mirador de Lau. And that's really kind of an interesting place. The name translates as a Moon Valley viewpoint. It's an ever-changing and vibrant color area. It's most spectacular, though, at sunset, so I seriously doubt people got a chance to really appreciate it. But because of that, it's one of Angola's top tourist attractions. It's a spectacular view that's just right along the coast, and it's where the escarpment has been reshaped by wind and rain. The escarpment basically is a big piece of chunk of crust that got pushed up, so you got this seam that comes up out of the ground almost. It's a big, like a wall, and it separates the lower land by a relatively different, pretty good sized height. And we're going to talk about some other escarpments as we go along and during our cruise. For those of you who live in New York, if you look across the Hudson River to New Jersey, there's a large wall of rock that you can see in some areas along that coast that's basically part of the escarpment that's left over from when North America broke away from Europe. We promised to look at the new continent that's forming as we speak, so if there's any real estate agents in the audience, I'd be happy to give you the dimensions and so on and how we can break that down into some good development. Anyway, it's tearing apart from basically what started a lot of the things to happen out here in the Indian Ocean at a place called the Rodriguez Triple Point, and it runs all the way up into the Red Sea. Now, by doing so, it's dividing the African plate into two pieces. Remember what I said earlier, where almost everything else seems to have broken away from Africa, and Africa just kind of sat there while it happened. The new continent is just currently being called the Somali Plate. That's because it sits mostly around the Horn of Africa, and it's basically the easiest thing for the geologist to recognize. Now, the African, Asian, and Antarctic plates all meet there in the middle of the Indian Ocean at the Rodriguez Triple Point. And that's where the whole thing started. The boxes that are shown, and you can see these outlined boxes there, they represent the amount of seismic activity that's happening around those plates. Now, this is the Great Rift Valley. It's kind of hard to see here, so I'm going to make a little thing to make it easier to see. It can be seen from space with the naked eye, and it's there that the plate is tearing or rifting apart, and ultimately it will start to fill in with water. Now, fortunately for Earth's inhabitants, mostly the animals and the people that live along the Rift Valley, the rate of geologic process is extremely slow. The west side of the new continent is along about a 3,700 mile long rift. There really isn't a separation of the continents, it's just there's vast bodies of water over the top of land. So if you think about all of these plates, a lot of them are still partly submerged and partly up where we can see them. Now, it appears that Pangaea broke apart, but Gondwana and Laurasia were separated by what was called the Tethys Sea. It later became known as the Indian Ocean and the Mediterranean. The Rheic Ocean formed and eventually became what we know today as the Atlantic. Now, we're going to talk a little bit about how these oceans formed. At the initial stage of formation of the African Rift, for example, a crack starts to form in the earth. And that's caused because pressure that's underneath the Earth's crust, the mantle, is actually pushing up. It's causing a pressure, and it's causing this upwarping. It's causing the land to get pushed up. And as that land gets pushed up just along that weak spot, eventually it'll start to crack. And as it cracks, it'll fall back in on itself. And it'll keep doing that, and it'll keep building up and building up and building up. And also it's starting to pull apart a little bit. And structural failures in the rock will occur, and it'll fall back into the earth as a rift valley. That's what caused the rift valley that we have in Africa today. And that will happen over and over and over again over millions of years. Then those narrow stretches of valley will just continue to pull apart until it runs the full length from one part of the plate to the next part of the plate, so that now you've got these two pieces that have a big deep valley in, and it continues to widen and it continues to deepen by that upwarping of material. And that goes on until it reaches an existing boundary of the sea. In this particular case, it's going to be the Red Sea and the Indian Ocean. And when that happens and that new sea level, that new floor is below sea level, eventually there'll be a break at the end. It's like breaking a dam. Everything will flood in, and the Rift Valley will fill with water. Now that body of water will continue to deepen as the plate movement continues to push the land farther apart. And all that little thing in the center will continue to push up, and the two parts will continue to spread apart. And the basin eventually become a mature ocean like the Atlantic. Now a small ridge will probably form in its center as the magma will continue to press up from within the earth, and that will cause a pretty good size undersea mountain chain that will be between the now new plate boundaries. Scientists believe that ridges all along the crest of the undersea mountains are just weak zones in the earth where the oceanic floor is being spread apart. New magma or molten rock from deep in the earth rises and creates pretty new oceanic crust. And that new crust, if you think about it, is what's causing the Americas to slowly move away from Africa. On the Pacific side, it's also causing Australia, New Zealand, and Asia to move away from North America, but they're not moving. They're just sitting there. Why? Because over there, there's a subduction, and we'll talk about that again. Now, this action over millions of years is responsible for these mid-ocean ridges. Now, that whole concept, after Wegener and the others, has become known as seafloor spreading, and it's evidence that all of that rifting once tore Pangaea apart. Now, why doesn't the Earth get bigger if everything is stretching like that? As I said, there's a process called subduction where one plate starts to slide under another plate. The biggest and deepest of those is in the Marianas Trench. So along the east coast of Asia, there are these huge trenches, goes off of Japan and off of Russia, all over in there, and that's where the Pacific plate is actually sliding down under the crust of the Asiatic plate, and it's keeping the Earth at the same size it has always been. And it is recycling all of that material back into the mantle. Now, as we sail along on this beautiful ship, it's pretty hard to get a sense of the great forces that are continuing to shape our world. When you think about it, we see things, we see rocks, we see trees, we see seashores, but you don't understand the dynamics. Now, if we happen to be lucky, I hope we aren't, but if we were lucky enough to see a really massive volcanic eruption, you would see one of those forces come into being to creating new land on our Earth. Now, many of those things are hidden very deep beneath the sea, and except for those occasional earthquakes or tsunamis or volcanic eruptions, we rarely, if ever, will encounter them. Now, from Gondwana to continental drift and the birth of the oceans, we live in a very, very dynamic world. Our cruise today and over this next, let's see, what do we got, a month left almost, is taking us past some of the most geologically important features on Earth. Now you have a better understanding, I hope. It's just a real brief snapshot of how all of this works, and so you'll be able to see the things that you're going to be able to see on our voyage. But all of that, the understanding of how that came about, comes back to Alfred Wegener and Ortelius and Snyder Pellegrini and all of those very early people who were brave enough to state what they believed to be facts when it came to the way the Earth was formed. Remember, Wegener was criticized, harshly criticized, for his theory, which has now been proven to be true. And with that, I would like to thank you very much. This will repeat on your stateroom television on Channel 9. And if you have any questions, you want to talk about this lecture, you want to talk about the shape of the Earth, probably not the politics thereof, but the shape of the Earth or any of our ports of call, you can meet me out for coffee and baristas. I'm going to go out there now to have a cup. So those of you who are staying for trivia, you could run out there, grab a cup, and come back in. Anyway, it's just down the hall for those of you who don't know where it is. I think everybody does. It's down there just outside the main dining room. And as I said earlier, Susie and I are always available for discussions and questions, and please don't hesitate to ask. So my next one will be in occurrence, and I'd like to thank you very much for your attendance.